Welcome to Study Loop.
So here we're going to use the conservation of mechanical energy. The center of mass is at the midpoint of the crossbar, and it drops by L over 2, where L is the length of any one of the rods. Therefore, H would be equal to L over 2. And we can say that the change in gravitational potential energy will be equal to the change, well, rather, it'll be equal to the rotational kinetic energy gained. So we can say that mgl over 2 would be equal to 1/2 times I omega squared, where the angular velocity would then be equal to the square root of mass times gravity times the length of any one of the rods divided by the moment of inertia. We can then say, since the rods are thin, the one along the axis of rotation does not contribute to the rotation. Therefore, all points on the other leg are the same distance from the axis of rotation. So we can say that the leg contributes a certain amount of rotational inertia, where the rotational inertia would be equal to m over 3 times L squared, where, of course, m over 3 would be its mass. We know that the crossbar is a rod that rotates about one end. So that if it's rotating about one end, this means that the moment of inertia of the rod, or we can say crossbar, would be equal to m over 3 times L squared divided by 3. This is equaling ml squared over 9. Therefore, the total moment of inertia would be equal to m over 3 L squared plus ml squared over 9. This is giving us 4 ml squared over 9. And we can then substitute this into the angular velocity equation and say that the angular velocity is going to be equal to, again, mgl over I, equaling the square root of mgl over 4ml squared divided by 9. And the angular velocity would then be equal to the square root of 9g over 4L. This is equaling the square root of 9 times 9.80 meters per second squared divided by 4 times the length of one rod, 0.600 meters. And we find that the angular velocity is 6.06 radians per second. This would be our final answer. That is the end of the solution. Thank you for watching.